Okay, so with basic dimensional analysis, for example, if we measure something like density, and this is going to be really the reason why significant units, I'm sorry, SI units, we call them, right? Um, so I just, let's see. Yeah, international system. It's like backwards. It's why I never even, you don't really have to know. I just, I never even knew what this stood for. I do chemistry. Like, I'm not a bad chemist at all, but it's just like, I just say SI units because when I see SI units, I just see it, right? I see what it actually is, whatever. So let me explain something. If we have something like density, is it on here? Okay, we can write density like this, right? That's going to be equal to the mass over the volume. One example, we might have the density. We look at my table actually, and I can use an example. Let's see, I'm not sure what units they're using though. Let's see. Let's see. I'll have to look up densities. Um, Now the common thing is like 1 milliliter is equal to 1 centimeter cubed, right? So that's okay. Yes.
Divided by the volume. Then does that mean that if finding the volume and density divided by mass?
No, finding the volume would be mass divided by density. Okay, let me explain something real quick. Give me 1 second. Okay, so what I was trying to get at, my bad, was was this. So let's say you've got. Let me look at one that's. We know that water has a density of 0.997 grams per centimeter cubed. So the density, and we abbreviate it like this, of water, you could like that, is equal to 0.997 grams per centimeters cubed. So, and sometimes we just say most people accept that the approximation is 1 gram per centimeter cubed for water. We usually always just use one academically. No big deal on that. It's pretty common to just use one for water. Um, and the density of, let's say, hydrochloric acid as a gas, you do a little parenthesis, or I guess I shouldn't say hydrochloric acid, but hydrochloric gas. That density is going to be 1.187 grams per centimeter cubed. But there's another thing we can call it. We can call it 1.187 grams per milliliter because 1 milliliter is equal to 1 centimeter cubed. So it's three-dimensional, right? It doesn't have to be an actual cubic block. So let's go to, let's see here. Right, and just to kind of drive a point home here with an AI summary, so you can see this, just to cite my sources, right? But yeah, I don't need to. But yeah, that's going to be that conversion there. So that's important because maybe we can come up with a problem where I want you to calculate something, right? So given, let's see, what can I give? Given the density HCl gas, maybe I'll use a different one. Let's use gold. Let's use gold. Given that gold AU, right, The density of gold
Yeah.
is a solid, of course. We'll just say that. No need to put it there because it's most common as a solid. That's going to be equal
It's
to
19.3 joules.
right, and it's going to be grams per centimeters cubed. Notice how I'm writing it like that. If I have a, let's see, a piece of gold that weighs, let's say, 21 grams. Calculate the volume. Of the gold piece. So then what you would write out is, you know your density.
Because you know it's 19.3 kilograms.
Yes. But here's what I'm getting at. When I do my chemistry problems, there's two ways to do them. Sometimes it's just what's the best way. Sometimes the mind likes to do things, Occam's razor. It wants to do it the quickest way that it can, or the most efficient way that it can, not quickest. So this is one way of doing it. Another way of doing it is you would write it out, but I like to start it out like how we do chemistry. We call this the ladder method. Because it's really convenient to cancel and know what you're doing. It's useful since most chemistry, or even physical sciences, involve SI units. So then if we start with 19.320 grams per centimeter. Okay, so this I already messed up. We put the grams in the top and we put its in the bottom like that. You follow me?
Yep.
And then so now I said that we had what? We've got calculate the volume. Well, I like to kind of over to the side, I like to write out that density is equal to mass over volume, right?
Yeah.
So I think that volume equals mass over density, right?
Right.
So if we want the volume, I already started this wrong, right? It's okay. It's okay to do that. You just got to erase it. So if we were given 21 grams of gold, and you don't have to like cancel the gold or anything like that for now. We're not doing any sort of empirical stuff or balancing quite yet. And since we know that we want volume, so I'm going to go ahead and shorten this out a little bit. It's not that long of a ladder for this one. I think that's all we're going to need actually. So then what I say is, okay, we know we want volume to be in centimeters cubed. Some answer, some number. So we need centimeters cubed in the top. So if I look at my formula, that means that's going to be like that, which means your significant units need to cancel like this. So grams, I always do the fraction if I'm doing it like this, right next to the, so then you're going to have your grams, but then the density is grams over centimeters cubed. If you keep change flip, these cancel and you get centimeters cubed and you know you're on the right track. So I like to do a little side work. That way it keeps me going in the ladder. So that means I need to divide it by the density. So I kind of write it backwards. I know that it's 19.320 grams per centimeters cubed. I know that it flips, right? And I put an understood 1 there for clarity, right?
So that means you have to multiply 21 grams and then you can do it, right?
Okay, let's not get ahead of ourselves. So the way this works is you multiply across and you divide the bottom as you go along, and you just keep doing it. That's what's really awesome about it.
Oh, wow.
But the most important thing that we're talking about, since we're talking about SI units, right?
Right.
Is that we cancel. That's why we write them out. It's what you have to get used to. So it made me better at math, actually. Chemistry did. We cancel the grams. And guess what? We're left with that centimeters cubed, which is what I wanted. Because there's nothing left to cancel, right?
Right.
And then we just do the math. Right, so then, geez, so many tabs. Hold on.
Sorry for getting ahead of you.
No, you're good. So, let's see here. No, that's not what I wrote. Oh my gosh, cloud chemistry. Okay. So I'm gonna get that calculation. What's that? 19.6.
19.3.
21 divided by 19,320. Got it. I know. I'm trying to remember the letter when I go to the next screen, man. So now I got to go back. I don't care about the decimal. Yeah. 19,320. 19,320. And you've got to get used to using parentheses in this course. And I'm going to give you an example as to why. Right? That's why when I'm teaching you math, when I taught you early college algebra 2, I said how important parentheses. It becomes extremely important in chemistry. If you're not using parentheses, you're going to make mistakes. The answer to this is going to be 1.08696 centimeters cubed.
Right. Yeah, that's what I got.
Now, here's where it gets interesting. The reason why that's important is because if I gave you, say, the mass of element nu, which is just a mythical element, just putting this up here, is 48. Hold on a minute. Yeah, 48 grams, right? How many? I'm trying to come up with a way to. No, I want a more involved question. Say the volume. Because I'm going to show you why it's important. I'm going to pick the best thing. So the volume, we'll say it's 32, let's say, milliliters, right? Which is also, and this is important, that's why we need to understand that, 32 centimeters cubed, okay? That's the volume of element nu. Now, what is the mass of element nu in, say, I'm sorry, I didn't mean to say mass, I'm so sorry. What is the volume of element nu in, think of a random one, in liters? So what is liters, right? That's how so first we have to understand what is, this is the question, the keystone, what is a liter measurement in cubic units?
I think you mentioned on the previous
1 liter is equal to 1 kilogram cubed, right? So this is where it's important. If I'm converting to liters, I need to first understand that that's 1 kilogram cubed, right? But why is that? So we know that 1 milliliter is 1 centimeter. Sorry, I am tripping. I am so sorry. I'm off my game today. I say 1 liter. I don't know why I said kilogram. I'm so sorry. Is 1 meter cubed. My bad.
Okay, that's what I thought.
Right. So then I know that. Right. Exactly. So if I have 1,000 milliliters, and I know that it's that 1 milliliter is 1 centimeter cubed, right? Then I have 1,000 centimeters cubed, right?
Right.
Um, I don't know where I'm going with this, but then I take that, and I know that if it's 1,000 centimeters cubed, right? I know that. Let's see, and I want to. Let's say I want meters cubed, right? Let's see, I know that 1 meter, one sorry, 1 meter cubed. And I'll put parentheses because there's like, how is it? 1 meter is 100, right? Wait, yeah, centimeters.
Yes. Correct.
Let's see. So in order to finish this calculation, notice how I'm engaging it like so, but it's not complete. What am I missing? Notice how I arbitrarily, even though it's not going to change these values, I need it in meters cubed because we need volume,
Yes.
right? It's not linear. Since it's not linear, we have to make these parentheses, don't we?
Right.
So we have to cube outside the parentheses because we need this to be centimeters cubed. That needs to, remember our exponent rules from algebra?
Yes. Yes. Yes.
Okay, I'm going to do that, right? I'm going to show you. 1,000 centimeters cubed. You got 1 cubed, which is just 1, right? That's why it works. 1 cube, meter cubed, that's just 1 meter cubed, right? So we really don't write this because we know that's just 1, right?
Yeah, that's all.
I just proved that. But what's important is the conversion. That gets that number ain't just 1. That's 100 cubed. And guess what? Now we can cancel our centimeters cubed. You know, you don't have to write the ladder on your starting value. If there's anything beneath the ladder, it's not 0, it's not anything. You just assume there's a 1 underneath it. We don't write it. We could have wrote the ladder method like this, right?
Right.
We don't need to put anything down there. It's empty, it's just empty. So notice how we canceled these, and guess what? We have to do the math. So the math states that we got 1,000 over 100 times 100 times 100 meters cubed. And we know we have the right calculation. We just need to calculate it, right?
Right.
So what this looks like is that these two zeros are going to cancel.
Right.
And then this 0 cancels with one of these zeros, right?
Yep.
So then that's going to be 100 times 10, which is 1,000, right? So that's 1 over 1,000 meters cubed. We can also write that as what? We can write it as a decimal, can't we?
Yeah, 0.0001.
Yeah, 0.001. That's right.
I did that in my head. I should not do that again.
That's good. So we know that that is equal to, yeah, that is equal to 0.001 meters cubed. But I ask in this example if we've got 32 centimeters. And that's just understanding these units. See, this was just understanding those units. This had nothing to do with the problem, right? Well, it did, but it didn't. This is kind of the kind of practice that you need. In order to answer this problem, right, then what we're going to do is we're going to put 32 centimeters cubed. They don't want to tell you centimeters. They might just give you 32 mils. You're supposed to know this. I'm doing it for the lecture, but so I know I need it in liters. So I know I need, let's see, I know I need meters cubed, right? So then what do I need to do? So I put, let's see, 1,000 centimeters cubed. Should be that. Just like I have over here. And I know for every cubic meter now that there are 1,000 centimeters cubed. Right? Or wait, hold on. Sorry. I'm messing up. Let's do this really easily. I know that there are 100 centimeters for every 1 meter, right? And then I know that I want cubic meters. So the way we approach this is we just simply do that.
Yeah, that is because I see on
And that's the best way to do it, right?
right.
So then now you've got this 32 over 100 to the third power. Oh, I'm sorry. I messed up again. I keep messing up my units. Wait, no, that is. Oh, I'm correct. So then I need to divide that by 100 cubed, centimeters cubed. Centimeters cubed cancel. And then I'm left with meters cubed.
Yeah, it's going to be 32 divided by.
Right. So now we got to think about this. This is 32 cubic centimeters, right? And 1 liter is like 0.001 meters cubed. So it would make sense that number needs to be really large.
Right.
So now if we do our calculations, you could write 100 3 times, you just divide it. Let's go ahead and take a look real quick.
You put 32.0 to make your life efficient.
Wait, say that again?
You know how you put the point 32.0? I love how you did that because it just makes your life easier.
Yeah. Thank you for that. Yeah, like common sense goes a long way. Your logic goes a long way in this course. So just to kind of recap what we did, the first thing we did, and I'm going to kind of lay this out for the viewer, is that we did our dimensional analysis here. No, we needed meters cubed, and then what we did is we realized this was 100 cubed to the negative 1 power, and then we just kind of looked at this, and that gave us, we did 100 times 100 times 100. The first gave us 10,000, and then that remaining 100 was there, and that gave us the 1 million. Sorry, it gave us the 1 million here. And then I knew I could write that as 10 to the 6, or 1 times 10 to the 6 to the negative 1, which is just equal to 10 to the negative 6. So then we put that there, and then we just go back 6 places.
Right.
And so now that's, so the important thing in this lecture is that you're doing your dimensional analysis right, because it's no longer linear. That means you have to invoke parentheses when you're doing these. And I often like to put it, also do it, even though it seems trivial, you need, what's important with significant figures is that it's not, you've got to track your work. It needs to become instinct. It's how you solve these, because you can have ladders that go on and on and on, right? So you want to make sure that you are doing these calculations as proficiently as possible. But yeah, that's kind of the beginning of understanding a few things here in chemistry. There's another thing that we're going to discuss real quick, and that has to do with volume displacement, right? So right, and we have things like units, mass and volumes, density units defined by, and the reason why we need to know our SI units is because of what I just discussed. If you didn't know, or if you need to, you could still, what's funny about chemistry is that you might think you don't know how to solve a problem, but oftentimes you can. It's these little things. You don't need to, as a person who knows chemistry, I'm not going to say I remember every little unit, but if you know what you're doing, you can always look up a conversion. Notice how 1 meter and 100 centimeters is something most people know. So if you want the cubic version, like the meters cubed or the volume, well, here you go. That's how you get it. You don't need to look it up. You need the more basic version. And that's important because when you don't know a few of your units, then this gets really messy. So,
like for example, like centimeters would be common sense. So, 100 centimeters was we know that to make it parallel, to make it linear, we need to use 100 centimeters to equal to 100 meters.
What was that?
have to make sure your conversion parallel. It's given for centimeters cube. It's common sense tells you that you use 100 centimeters. Uh, you know what I mean, right?
Yes, yes, yes. That's logic. Yes, you're using what you know. But what's cool about this is the method's universal. So if you're missing certain things, you don't have to see. This is what. Let me not go on a tangent, but I will say something that's really important for the audience. And it does. Let me just be fair to humanity. It does irritate me when people think that they have to cite or know something. And forgive me for anybody out there who's listening who we've had any sort of discord on that, because it is quite a pet peeve. And it's not that citation is a bad thing to do. You should cite whenever required, but you don't need to cite stuff like this. But what I'm really getting at is, do you really need to know every little thing when you know the method works to so many of those things? And the answer is no. You need to learn how to do it. You need to know how to do the form and the function, how to do the math, and that gets you to you proving your problem right, or in the right way, or you solving your problem. So you don't need to cite, oh, I know that 1 meter cubed is, or I know that 1,000 centimeters cubed is 0.001 meter cubed. If you knew how to do the math, you wouldn't need to memorize that, right? So let me explain, right? So let's say that the viewer did this, right? Just to show what you don't want to be doing all the time, right? You don't want to look up every single value, right, on Google, right? People do this, and that's why all they do is just regurgitate. They're not actually solving a problem. It's impossible to memorize every single unit. That's silly, right? But knowing your linear gets you there, and that's the point. That's the whole point of chemistry, right? It's the closest thing to writing an essay. You're staring at the white wall, Hemingway said. You have to solve it any way possible. So let's discuss.
Anakin, Chancellor Palpatine is evil! From my point of view, the Jedi are evil. Well, then you are lost!
This is the end for you, my master. Ninja vanish!